Hello. In today's video, we'll be talking about analog encoders. They can be purchased online on electronic specialized websites. Encoders measure the angle and the change in angle of an axle. Standard FTC legal motors have digital encoders built into them, and you can use the encoder class to drive the motors a certain distance. However, if you abruptly accelerate, the wheels may slide and the sliding distance isn't accurately recorded in the encoder. This is why more advanced teams use so-called passive wheels. Passive wheels are made up of omni wheels and encoders. The main thing to know is that passive wheels aren't physically controlled by the rev hub. They just roll around and the encoders record distance very accurately since the wheels don't slide. Passive wheels allow the user to speed up their robot during the autonomous phase while maintaining an extremely high level of accuracy. Now I'll explain how to set up a single passive wheel. Here's our setup, which includes a 3D printed casing that holds our Omni wheel and is connected to our encoder through a hub. Now I'll explain how to program the encoders. First off, we need to understand how the encoders measure the angle. For analog encoders, the encoder has an input voltage and an output voltage. Depending on the angle of the shaft of the encoder, the output voltage is returned back to the rev hub. This means that as angle increases, the voltage goes up and down in a specific manner. As you can see, within a 360-degree subsection of the graph, the voltage and angle are proportional. We're assuming that the rev hub reads the voltage returned from the encoder at a sufficiently high rate. More on this later. Basically, to be able to determine the total angle displaced, we'll write a loop method to check the voltage continuously, convert it to an angular value, and add it to the total angle displaced. My code is on our GitHub page, and the link is in the description. As shown in the picture, we need to set up an array list and continuously add the voltage values as mentioned before. The angle change method gets the two most recent voltage values from the array list, and in most cases simply takes their difference to find the change in voltage and converts it to an angular distance value. This works when the voltage goes up or down the slope. However, since our graph has many large drops in voltage every rotation, we need to either add or subtract the maximum voltage, depending on the direction the encoder is spinning, to the difference in voltage to simulate an extension of the slope. Then in the loop, we add the final difference to the total angle change. Problems may arise if your wheel speed is too high, the wheel size is too small, or your loop update rate is too slow. To determine if you may have problems, first divide your maximum robot speed by your passive wheel circumference. Multiply the value by 2. If the final value is greater than your loop update rate, then you may not be able to capture the actual change in angle by your passive wheels. This is a problem because the hub only knows the current angle of the encoders, but not its relative position from the last recorded angle. So your encoder value may jump from one hump to the next without the hub knowing. To ensure that the loop update rate is high enough, we can use a class called bulk data read, provided by OpenFTC's GitHub page revextensions2. The class allows us to gather all the sensors reading in one round rather than asking for RevHub for each reading individually. This is a fairly simple to integrate into your code using the install instructions and an example code which is also on their GitHub. Thanks for watching. See you next time.